Hi everyone. So welcome to this lesson for Calc 1. We're going to be looking at the precise definition of a limit in this particular lecture. And where we're going to start off is with the actual definition of a limit. The precise definition says, let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit of f of x as x approaches a is L. And we write it as the limit as x approaches a for f of x is equal to L. And here's where the difference actually happens with the definition that we presented for the definition of a limit back in earlier chapter 1. The second part of this definition then says if for every epsilon greater than 0, there is a delta greater than 0, such that if the absolute value of x minus a is greater than 0, but less than delta, then we will find the absolute value of f of x minus L to be less than epsilon. Wow, now that's a lot going on there. Okay, so that's a lot going on. So what we want to do is we want to break down that statement just a little bit more. And the way we're going to break that statement down just a little bit more is we're going to start looking at this function f of x. And I want you to notice that I have three different versions of f of x here on the screen. The first function on the left-hand side, what I did was I found I identified some a value on this x-axis. That a value will then be an evaluation for the function, and then we will be able to establish that we will have some function L, some output L. Now, what does this mean for us in terms of an epsilon-delta definition of the limit? Well, what that means is that we're going to take this interval where I've bounded my value of a, and what I'm going to do is I'm going to start shrinking this interval. Smaller and smaller and smaller. And when I do this, I am getting closer and closer to the value of a as I'm approaching a from both sides. Again, because I am shrinking that interval. Well, what that implies then for us is that as we do this, all of the outputs for the function will also start making small and small and smaller intervals around this converging limit, which we call L. So what does that mean then? Well, that means that as long as we can define some interval around A, and as long as we're able to shrink that interval small enough, then we will be able to find some sort of limit if that interval can produce it. Now, the function aspect of this, or the function value for f of a, does not need to exist. And that's where the second picture comes into play. For the second picture, we have an open circle, or in this case, that the value of a is not defined for the function f of x. Now, if you take the same approach, then naturally, shrinking this interval smaller and smaller and smaller so that this interval completely engulfs a from both sides will naturally lead to the interval on the y values getting smaller and smaller and smaller, and once again encompassing that limit. Therefore, the limit will still exist. However, once you get to the very last portion here, or the very last picture, what's going to happen here is if we start then shrinking this interval smaller and smaller and smaller and smaller, you will see that we are not getting to one specific value. Simply because the interval on the x-axis will converge to this value of a. However, this value, or the limits, will actually converge to two different limits. One limit will be from the left, the other limit will be from the right. And as we see from before, from previous sections, the limits for the left and right hand must exist, and they must be the same limit. And in here, we can see that the interval along the y-axis stops after a certain point, meaning it does not converge to one singular number like in the previous two. Therefore, on this last value, the limit does not exist, or for this last function, the limit does not exist. So we have to make sure we keep that in mind. Now, that's the visual representation. Now, in order to jump into these proofs, what we're going to do is we're going to first go through an example to make sure that we understand what's happening with this epsilon and with this delta. So in order to extract this or to illustrate this, we're going to go to this example that says use the given graph of f of x is equal to x squared to find a number delta. So again, we're finding a number delta such that if the absolute value of x minus 1 is less than delta, then the absolute value of x squared minus 1 is less than 1/2. So it's important to extract what they're telling us here. What they're telling us here is that they are actually giving the epsilon value. This portion that I highlighted, the absolute value of x squared minus 1 is less than 1/2. This portion here, they're giving us f of x. They're also giving us the limit value, and they're giving us the epsilon value, which means we're going to be able to extract this and put an interval around the y values. So if we know that this is the limit is equal to 1, well then putting an epsilon interval around that would mean that we are increasing by 1/2. So what I want to do at this point in time is analyze that I have this epsilon value and this epsilon value here as well. In doing so, we've now created this interval. And what we want to do when we create this interval, we now want to find what are the outputs here. So I'm going to do these in different colors. And I want to now find out what interval is this on the x-axis. More importantly, which side of the interval? Is it the left side of 1 or is it the right side of 1 on that interval that is closest to 1? The closer we get to 1, the better the delta approximation will be. So in order to do this, we're going to be using this particular value here, this function for x squared. So what I want to do is I want to then extract what is this value down here for the left endpoint of the interval, and what is the value for the right endpoint of that interval. Now, instead of writing question marks here, we can go through and we can identify it a little bit more properly. We'll say the leftmost interval endpoint will be x sub 1, and the rightmost endpoint will be x sub 2. Now, because these values will be evaluated onto the function, we're then going to be able to extract that if we take the function of, let's say, f of x sub 1, this is going to be substituted into the function itself, which is x sub 1 squared. However, we already know the output. The output is the y value of 1/2. Now, if we want to solve for x sub 1, all we need to do is take the square root. Be very careful when you take the square root, simply because the square root, as we can see, will produce two different values. We want to make sure we only focus on the positive value, which means that x sub 1 will equal to the square root of 1/2. And we'll keep that in our back pocket for now. Secondly, we also want to look at f of x sub 2. F of x sub 2 we're going to make sure we substitute that into our function. The output for f of x sub 2 is going to be 3/2. Which means, again, only focusing on the positive x value, because again, we're able to have two values. Focusing on the positive x value, we get that x sub 2 is equal to the square root of 3/2. As such. Now we're going to need these approximations. So we want to make sure that we get an approximation for the square root of 1/2. So let's go ahead and let's get that approximation really quick. So the square root of 1/2, we're going to approximate this to be about 0.707. And the square root of 3/2 will approximate to be about 1.225. Therefore, we found these values. We have 1.225, and we also have 0.707. So now, which one of these values is closer to 1? Well, in order to figure that out, we then need to find the distance. And this is where the distance value starts coming in for that delta. Okay, and again, we want the smallest value for delta. So let's go through and let's start looking at the smallest value. And remember, when you're looking at distance, you're just going to be looking at the absolute value of that difference. So let's look at this. I want x sub 2 minus 1. Okay, that's going to give me that first distance on the right. And x sub 2 minus 1, x sub 2 was 1.225 minus 1, which means we're going to get 0.225. I also want to investigate as 1 minus x sub 1. And to find this, 1 minus 0.707. So you then just have to perform 1 minus 0.707, and you will wind up with 0.293. Now, which one of these values is closer? Well, the smallest value will be the closest value that we want. Therefore, delta, or the delta that we want, is going to be 0.225. And now that 0.225, again, is this interval that we're looking for here. That's the delta value, or that interval length. So again, every time we're given an epsilon, we want to make sure that we can find some sort of delta for it. Or more importantly, if we're given some delta, can we find some epsilon for that value? Great. Now, what we want to do is we want to start working more with the limit definition for the functions that we're going to be presented with. In order to do this, we're going to work with a few examples. And the first example that I want to work with is going to be this example, that I want to prove the statement using the epsilon-delta definition of a limit. Now, what does this mean for us? Well, for part A, we're going to be looking for the limit. All right, so the limit as x is approaching 10 for the function of 3 minus 4/5 x is equal to -5. Now, this one might be a little bit on the tougher end, but I highly think that you all will be able to work with this. So what we want to do then, we want to start our proof in this manner. We want to say let epsilon be greater than 0 and delta be greater than 0. Awesome. That's where we want to start. Once we have this, then we can go through and we can start using the definition of the limit. The definition of the limit says that if we have if we have an epsilon greater than 0, then there will be some delta greater than 0. So again, we've already stated that. Now we're going to state the given, which is that the absolute value of x minus a will be less than delta. And that's where we're going to begin. So I'm going to say, consider the absolute value of x minus, and a in this particular case is going to be the value that the limit is approaching. The limit is approaching 10. And this is going to be less than some delta. Again, we don't know what delta is. We don't know what delta is, but we will be using this particular piece. Now, the way you want to structure these arguments is that you want to work with some scratch work. Specifically because if you try to go forward or straightforward, you're going to find that it's going to be rather cumbersome to actually get to the point that you need. So instead, we build this scratch work, and this scratch work is kind of like looking at the finish line and knowing what you need to do in order to get there. So, in the scratch work, we know that the overall goal is to get that the distance between the function and the limit will be practically negligible. It'll be less than some value of epsilon, where epsilon is greater than 0. In other words, it can collapse down to 0 under the limit definition. So, that's our overall goal. But in order to get this goal, we need the function. Well, what's the function that we're looking for, or that we're looking at? That function is 3 minus 4/5 x. Oops. That's my function. And then I need minus the limit. The limit is -5. Now this has to be less than some epsilon. Again, we're just doing this so that we can try to anticipate what we might need. We'll simplify at this point in time. So 3 minus 4/5 x plus 5 less than epsilon. Add the common terms. 8 minus 4/5 x less than some epsilon. Now we need this particular piece here. And we need that particular, let's say, piece so that we can be able to extract some sort of value that will match what we have on the left side of the screen. So what I'm going to do is I'm going to simplify this fraction by factoring out a 1/5. So I factor out a 1/5, which means factoring out a 1/5 from this 8, well, it might be a little bit weird to think about it, but try to think about it the opposite way, that if you multiply 1/5 times a number, 1/5 times a number should give you 8. What is that number? Well, if you guessed 40, yeah, that's it. Because 40 divided by 5 should get us 8. And that's exactly right. So looking good so far. Oops. So looking good so far. Now, I want to then multiply both sides by 5. Since 5 is a positive number, that's going to be nice. And in this sense, we're going to be left with this. Notice this side almost looks identical to the side on the proof. One more fine tune before we carry on to the proof. I now want to factor out a negative 4. If I factor out a negative 4 from my binomial, I'm now going to be left with x minus 10. And this is all less than 5 times epsilon. Now I can't just multiply by negative 4 on both sides. That's not the way it works. However, I can do the multiplication here of the absolute value of negative 4 multiplied by the absolute value, let's clean this up a little bit, multiplied by the absolute value of x minus 10 is less than 5 epsilon. Absolute value of negative 4 is just 4. So that's kind of nice, which means that x minus 10 must be less than 5/4 times epsilon. And that is where we want to go. So, looking at the left-hand side of the screen now, the left-hand side of the screen says, hey, we're starting with the difference between these x values and the number 10, and we want that difference to get smaller and smaller and smaller. Well, what is the delta value that we need to choose in order for this to start working for us? The answer to that is here on the right-hand side of your screen. So that value, I'm going to complete the proof sentence now. Consider the absolute value of x minus 10 is less than delta, and I'm going to give delta the value of 5/4 times epsilon. Now, when we're working with this, so we can say, let's say now, we're left with the absolute value of x minus 10 is then less than epsilon, we already said, but then we said epsilon is going to be replaced by 5/4 times delta. Sorry, delta will be replaced by 5/4 times epsilon. Now all I have to do is multiply both sides by its reciprocal, which will then get me 4/5 multiplied by x minus 10 is less than epsilon. Distributing, I now get 4/5 multiplied by the absolute value of x minus 10 is less than epsilon. And here's the trick. Here's the trick, everybody. The trick here is that these two statements that I will be highlighting right now, the first statement, this one, and the second statement, this one, they are exactly the same statement, because the absolute value will be able to eliminate the factor of -1. It turns out that both of them are equivalent, which then tells us that if they are equivalent, well, I can keep working with the last statement. And the reason I want to keep working with the last statement is because when I distribute, I now get -4/5 x plus, in this case, 10 times 4 is 40. 40 divided by 5 is 8, is less than epsilon. And as you can see, we keep getting closer and closer to this difference of f of x minus L. So all I have to do now is just keep working with that. I now need to decompose this number 8 in terms of the number, or sorry, in terms of the function value that was given to me as 3 and the limit output of -5. Well, that turns out to be kind of nice, because then 8 is now decomposed into -3, or sorry, +3, making sure I got all these, +3 plus 5 is less than epsilon. And again, our overall goal is to get that f of x minus L. Well, if I keep working and rearranging my terms and then rewriting one of my values, I'm able to extract this piece here. And this now gets me that my difference between my function value and my limit is less than epsilon, where I initially started with my x interval saying that that distance for that interval around 10 must be less than some interval that's caused by delta. Choosing the right delta now assures me that I will be able to find that epsilon. Therefore, we can conclude that the limit as x is approaching 10 for the function of 3 minus 4/5 x is equal to -5. And that is the end of the proof. And so when you're looking at your scratch work is sort of the basis or the map to this proof. And if you can follow that map, it will lead you to where you need to go. Again, the scratch work is kind of like working backwards, working from this ending point and seeing what you need to do to get there. Okay? At no point in time, I will repeat, at no point in time will you submit the scratch work as your proof. It's okay to have the scratch work on the paper because that to me then signifies that you were trying to anticipate what needs to happen. However, if you turn in that scratch work, the part that's on the right-hand side of the screen, as part of your proof, chances are you're not going to get points for that question. So please be very, very careful and be very, very mindful of that. So let's look at one more type of proof, and this is going to be part B. So for part B, we want to show that the limit as x is approaching 2 for the polynomial x squared plus 2x minus 7 is equal to 1. We want this specific proof. Okay. So we're going to start off the exact same way. Starting off the exact same way, and we'll see if we can pull this off. If not, we might need a little bit more tools at our disposal. So let epsilon be greater than 0 and delta be greater than 0. Then consider, again, we always start with the x-axis, the absolute value of x minus 2. What are the x values approaching? They're approaching 2, so we want that difference to be small. This difference will be less than some delta value. Will be less than some delta value. And now we need some delta value. So now we need the work to show what delta value we are going to need. And that's where the scratch work comes into play. So let's start working. All right, here we go. Remember, start off with your goal on the scratch work. Take your function. Your function is x squared plus 2x minus 7, and subtract the limit value, because again, what you want, or what we want, is that this specific distance between the function and the limit will be less than some epsilon. Well, if we take this, then we get x squared plus 2x minus 8 is less than some epsilon. Now this polynomial, or this trinomial, can then factor as such. And now this is where we're now left with identifying that polynomial. And once we've factored this polynomial, look at the left side of the screen where we have that consider portion. It says that we need the absolute value of x minus 2 to be less than delta. Well, we have x minus 2, and we have it right in here. The only problem is that it's being multiplied by x plus 4. Well, let's alleviate that really quick. I'm going to alleviate that by factoring, or let's say by separating my factors. I have x plus 4 as one factor and x minus 2 as another factor. They're both inside of the absolute value, which means that if they're multiplying inside of the absolute value, it's the same process as if we take the absolute value of each individual factor and then multiply them. So in this particular case, we're going to keep this in mind, and we have this now. However, we can't exactly divide by x plus 4. All right, so we can't divide by x plus 4 because our epsilon needs to be some numerical value. And if we divide by the absolute value of x plus 4, then epsilon or delta will no longer depend on some constant. It will depend on what variable we have for x, which will be a big issue for us. So we now have to figure out how we are going to work with this value of x plus 4. All right, so let's start working with that x plus 4. So what I'm going to do is I'm going to put a pin on that work. Okay, so here goes my pin. Looks like one of those push pins that you push into a push board. So there's my pin. Now, once I'm working with this x plus 4, now let's do this in a different color. That way we can signify that we're doing this separately. So we have x plus 4. There we are. Okay, so what we want to now do is we kind of want to go about the bounding to make sure that we can take this x plus 4, and we have to make sure to, let's say, find a certain bound that as this polynomial keeps getting closer and closer and closer to 2, that this value will work for us at all times. Okay, so let's go ahead and let's start. I'm going to begin here, the absolute value of x minus 2. I want to make sure I'm close enough to this x minus 2. Now, what's a close enough distance? I will leave that up to you. You can say that this distance will be less than 5, less than 4, less than 3, less than 2, less than 1, less than a half, less than 1/4, less than 1/8, whatever number you'd like. At the end of the day, as long as you choose one number that's fairly small, you'll be okay. For simplicity, how about we choose 1? Okay, so I want this distance, the x minus 2 value, to be less than 1, which means if I apply my techniques from algebra, I have this new interval. Once I have this interval, then I can add 2. Once I add 2 to my interval here, my inequality, I will get 1 is less than x, which is less than 3. But again, I'm not looking for my values to be bounded for x. I'm looking for my values to be bounded for the absolute value of x plus 4. So then what can I do in order to get x plus 4? I can take 4 and I can add it to this inequality. So if I add 4 to 1, then I get 5. If I add 4 to x, I get x plus 4. If I add 4 to 3, then I get 7. And this now gives me a bound for the numbers that I need. Now, which bound do we want? Well, at the end of the day, what we're looking for is to make sure that we're able to bound this value for x plus 4 as tight as we can. So what we're going to do is we're going to mimic kind of what happened here on this line, where we want a numerical value to be bounded up top and its opposite value to be bounded from below. So what I'm going to do in this particular case is I want x plus 4 now to be bounded by 7 and negative 7. Now, because this because this inequality just says that 5 has to be less than x plus 4, that's great, but can we bound it from below by -7? Sure. Then this inequality up top above this one still works. And therefore we don't lose any interesting values. And now having it in this form, we can now say that the absolute value of x plus 4 must be less than 7. Check that out. That is awesome. So now that we have that absolute value of x plus 4 is less than 7, now we can go through and we can interpret that substitution back where I put the pin in the work. So let's remove the pin. So pin removed. Okay, so now that the pin is removed, we can just keep going now. So let's keep going. The absolute value of x plus 4 times the absolute value of x minus 2 is less than epsilon. And if we make the substitution here, and making this substitution kind of feels off if you think about it just a little bit more. But I will explain when we keep going with the proof as to why it won't feel too far off from where we're at. Okay, so making that less than 7, there we are, which means that the absolute value of x minus 2 must be less than epsilon over 7. And remember, if you chose a different value other than 1 to bound your x minus 2, this value that we have for epsilon divided by 7 could be anything else. Okay, so please make sure that you choose any value that you'd like. I only chose 1 just to make it easier on us. So now that we got everything that we need, all we need to do is finish the proof. So I said that we needed a delta value, and we found one. However, there's actually 2 delta values at play here. 2 different delta values. Number 1, I want either my delta to be less than 1, my delta to be equal to 1. That way this inequality will hold, the one on the right-hand side. Or I want it to be epsilon over 7. And what I mean by saying that delta is equal to min of that set, it means that delta is equal to the minimum value of 1 or epsilon over 7. Therefore, epsilon can take on one of those values. Whichever value it takes on, it will automatically get us the correct answer that we need. So, we're going to keep going. So now, we're going to start building the work. X minus 2 is less than epsilon over 7. Say that happens. Well, if this happens, let's keep going. So what we're going to do is multiply by 7, which is less than epsilon. Now, what's going to happen here is I'm going to say at this point in time, let the absolute value of x plus 4 be less than 7. Now is when that absolute value, or now is when that feeling comes into play that I said on the right-hand side. Some of you might have a feeling that it doesn't work quite well if we just replace the absolute value of x plus 4 is less than 7. Now it should feel a little bit more comfortable, because if we're replacing this 7 as a part of the proof as the absolute value of x plus 4, then we know 7 must be greater than the absolute value of x plus 4, and replacing that will also be less than this quantity, less than epsilon. Thus, we will arrive at x plus 4 times x minus 2 is less than epsilon. Well, let's distribute now. So distributing here, we now get x squared plus 4x, which will 4x and then negative 2x will get us 2x, minus 8 is less than epsilon. And if we decompose this factor of, or this coefficient of negative 8, then we're going to be left with x squared plus 2x minus 7 minus 1 is less than epsilon. And this is where we want to be, because now we have the function minus the limit is less than epsilon. That's great. Now we can keep going. So let's keep going. If we keep going, well then that's going to lead us into a natural point to say, therefore, the limit as x is approaching 2 for the function x squared plus 2x minus 7 must be equal to 1. And that's what we had at the very beginning that we were trying to prove. This is a little bit more intricate, okay? Now, we did choose one of those minimum values to be epsilon over 7. Some of you might be saying, well, what if the minimum value was 1? Well, if the minimum value was 1, then we're still going to be able to bound it by using the technique over here in green, which is going to lead us to the exact same spot. So either one that we choose, either value that we choose for delta, we're always going to get the same answer, that it does actually converge and that the limit does exist. So this is a technique of using the precise limit definition to find limits. Now, I hope you all enjoyed this lesson. If you have any questions, again, feel free to contact me or to post any questions on the general discussion in class. And I will see you all for the next one, where we will be talking about continuity of a function. Till then.